Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. I thought I'd take a moment here today to make a couple of short videos about some interesting little side projects I have looking at some of the issues relative to structure on these ultra lightweight sailplane designs that we're working on these days. Many different ways to use these materials to build these aircraft and different ways of arranging them. Many have never been tested before. Many haven't even been thought of yet. It's an area of very interesting exploration, at least fascinating to me. Now, one of the issues that has been around for a little while is the uh, the actual configuration of the sandwich panels that we make. The D-tubes are generally a sandwich panel configuration, and you have many options of materials and how to use them to make those sandwich panels. And what we want on the sandwich panel is both strength and durability. And usually that means having fairly decent stiffness also. Uh, the key part of sandwich panels are you mustn't ever allow the skins that go on either side of the core material to buckle. If they do buckle, all your structural strength is gone. And it's over. That's when you start using the parachute. And there have been some interesting problems run into in the past. Uh, some designs have actually used this honeycomb core material. Now, if I hold this up a little closer, this isn't actually honeycomb shape here. This is a rectilinear core, but it's the same material. It's a Nomex core material, and Hexcel makes this. And this particular shape of of the cells, the little shapes, is so that it's easy to bend. This is a very flexible core material, more in one direction than the other. And if you're making leading edges, this is the stuff you want because it'll go around the mold very easily. The drawback is this is probably 2 or 3 times the cost of the actual honeycomb core material. Now, honeycomb core material looks like, do I have it on this one? Yeah, it's on this one. There's honeycomb core material right there. And the performance of these two is about the same in terms of a finished panel. It's just that this material is much more expensive but much easier to work with on tightly curved surfaces. This can roll up really small. You know, you can go around just about any shape with this. Not particularly great on compound curves. The original honeycomb core does a little bit better at that. So normally what gets done here is that you wet out the fabric, right, with epoxy resin, and you have a skin on each side, and you vacuum bag the thing together. Now this particular piece that I have here has some 1.8 ounce Kevlar on one surface only. I was experimenting with some other stuff, and it turned out to be a handy sample to keep around because it's easy to look at how the whole thing goes together. Now, the main reason for using the honeycomb core, despite its phenomenal cost, a sheet of the stuff can cost $200 to $400 easily, and a sheet's what, 4 foot by 4 foot, something like that. It's very expensive, but it has tremendous compressive strength this way because this is made out of a Nomex paper, and it has resin impregnated on it. Phenolic resin impregnates that paper in this direction against the surface because it's a bunch of little walls of this Nomex paper. It has incredible compressive strength, way more than any foam that's out there of equivalent density. This is only 2 pounds per cubic foot for this foam core material, really light. The foam that I'm using on my wing currently is 3 pounds per cubic foot, so 50% more. It's like, Raul, why are you using the foam and why aren't you using the Nomex? You must just be cheap. And I go, no, it actually has nothing to do with it. Anybody who's played with this stuff or put it on a glider or any aircraft knows that there's issues with using honeycomb core material that we run into as ultralight aircraft, but its general usage in the aerospace industry never ever encounters it. And that's the fact that our skins are often only one layer of fabric thick. And it might be 5.6 ounce carbon fiber, or it might be 1.8 ounce Kevlar. By the time we get one layer of fabric on each side, we have a sandwich panel that's plenty strong enough. In fact, in some cases, it might be over strong enough. And so it's not like we can go put multiple layers on here. And what you end up with is skins that can do this quite easily. And if they debond from the honeycomb, oh, there's almost no peel strength. You can just grab this and just peel this stuff right off. There's nothing to it. Like, wow, that's not glued on there very good. Now, how come the sandwich panels in the aerospace industry don't have this issue? Well, it's because they're like 4 or 5 layers thick on each side. And when you don't have this flexibility in the skin, it can't peel off. You can't get an edge up. You can't get a buckle in the middle. You can't get it to buckle. And therefore, you're not dealing with the peel strength of the adhesion to the core. We are. Because these skins are so thin, if you load up this sandwich panel enough, you could get a little buckle in the middle here somewhere like this where it pops loose from the honeycomb core, and then boom, you're over, it's done. In fact, it's actually happened. There was a glider, hang glider, that's flying at Point of the Mountain, Utah. And I believe it was a case where they had bumped the D-tubes previously in transport and either cracked or buckled the carbon fiber skin ever so slightly, didn't realize it, it's covered up with the fabric that's on the wing, and when it was put under significant stress beyond normal flight regime, I think there was some aerobatics being done or something like that, the wing failed because the skin just peeled right off the Nomex honeycomb core. Very bad situation. So I think most everybody now that's producing some type of aircraft that has a sandwich panel construction is using foam core. Because with the foam core, you get much more adhesive area. You look at this, there, I have a sheet of very smooth, small cell foam, or I have all these open cells. Now, one of the drawbacks is the foam is, if you wet out the fabric on the foam, the epoxy resin goes into the foam, and that resin actually can weigh more than the resin that's in the one skin that you put on there. So if you've watched my videos, you know I use special techniques to wet out the fabric separately, leave enough extra resin on it to bond to the foam. Drawback to the foam is it doesn't have but a fraction of the compressive strength that the Hexcel honeycomb core has. And it's very easy to dent it. You can dent it with your fingernail, bump into a rock, it's dented. It doesn't really happen with this honeycomb core. Honeycomb core, because of its incredible compressive strength, is highly resistant to being dented. In fact, if you go so far as to actually force the denting, you're popping the bond loose from the honeycomb core. Anyway, so pluses and minuses on the foam core, pluses and minuses on the honeycomb core. Another minus on the honeycomb is this can eat up a lot of resin from the fabric, because in each little cell you get a little meniscus that goes up and attaches to the side of the cells. And that's a bunch of resin that you don't necessarily need. You need a little bit of it, but not too much. And how this stuff is generally designed is to use pre-preg fabric, which has a predetermined amount of resin in it that is sufficient to bond it to the core, the honeycomb core, and have the fabric at the appropriate density and wet out. It's all been predetermined. Well, for us home builders and for aircraft that you only make a few of, using pre-preg is problematic because you need an autoclave to do it properly. Now, I think I don't know if the Aerotrix uses honeycomb core. I know the Swift uses foam core, and they're produced in factories that are just set up to build composite components, so they have autoclaves, and they can do it the right way with pre-preg. At home, much more difficult. So you can end up getting a lot of excess resin here if you're using the honeycomb core. So I was thinking, how do I gain the advantages of both of these materials and make the best use of both? How do I stiffen the skin enough to prevent it from being able to peel away from the surface so easy? How do I provide it with more bonding area, yet how do I get the compressive strength of the honeycomb core? And here's my plan. I'm going to run some experiments, and we're going to run a video later to see how it works out. I am going to put, when I do the layup, I'm going to do a layup with foam, Nomex core, and another sheet of foam over here, the thinnest foam that I can get, which I think is 1 millimeter. And then I'm going to put a composite skin on this side and composite skin on this side. So one layer of composites, foam, honeycomb core, foam, another layer of composites. Now, 2 layers of this foam is about the same as what's getting used in terms of weight for our foam core sandwich panels, approximately. And I'm hoping that when I put this in a vacuum bag, that the foam is going to be pressed down into the into the foam. That the honeycomb core will press in here a little bit when it gets enough load on it. Maybe I have to do it ahead of time with a rolling pin. But I can see I made some little dents here because the edge of the cells is fairly sharp. The paper is very thin, yet very stiff. So if I can get this honeycomb partially embedded into the foam, then it's going to have lots of bonding surface between the foam and a honeycomb. And the foam is going to provide lots of bonding surface to the composite skin. So everything will be nicely bonded together, and I will have gained the compressive strength of the honeycomb in the center of what is a 1, 2, 3, 4, 5 layer sandwich panel made of various materials. Is it going to work? I don't know. I got to run an experiment, see what happens. Probably won't work the first time or second or the 5th time, but I might get it to work. And it'll be interesting to see what happens, to see what the weight of the panel is, to see how stiff it is. I'm not sure it's going to prevent the denting of the outside surface unless I get the honeycomb pressed well into the foam, where the honeycomb's very close to the outer surface of the foam. This foam is pretty resistant, so I don't know if that's actually going to happen, but we'll see. It'll be interesting. And that way, we'll have a sandwich panel that is, well, this is 2 pounds per cubic foot. This is 3. And overall, the core of the sandwich panel will be thicker. The skins will be the same thickness. And that should allow me to realize a sandwich panel that's much stiffer than a single core material sandwich panel of the same overall thickness. So I might be a push on the weight of the core overall to something that's a thicker panel, but gain the stiffness that's associated with a panel that's taller or thicker, and retain the superior bonding of the composite skins by keeping the layer of foam in between. I think probably the best thing to put on here would be Rohr cell type foam. You can get that very, very thin. It's a tad brittle. I'm not sure how it would work out, but it's just really expensive, as most aerospace or aviation things are. The best solution's really the most expensive one. I'm going to try to do something that's not quite so expensive. So, an interesting project, and we'll see what turns out of that, and I'll come back and let you know. And as I always say, fly safe and bye for now.